The naive approach for multiplying two integers in sign and magnitude representation mimics the algorithm we generally use for decimal numbers. We multiply the absolute values of the two operands, and then we determine the sign of the result based on the operand's signs. Here we show an example using -13 and +11. As you can see, we first multiply the binary representations of the absolute values 13 and 11, thus obtaining 143, and then we assign the minus sign, since the two numbers have opposite signs. If we look at the hardware implementation of this method, the module includes an unsigned integer multiplier, like those analyzed in the previous video, and a combinational circuit to compute the sign. This method, although natural when using sign magnitude representation, becomes inconvenient and expensive when dealing with numbers represented in 2's complement, similarly to what we discussed for addition and subtraction. Indeed, we would prefer a direct method for multiplication in the same way as we perform addition. However, this is not possible in a straightforward way in 2's complement, since the binary representation of a number, and in particular the most significant bit, represents sign and magnitude together. As a consequence, this requires modifying how the partial product matrix is generated, while properly accounting for the sign of individual terms within the matrix. In this video, we introduce two methods for multiplying numbers represented in 2's complement: the sign partial product method and the Booth algorithm. The first method is based on the idea of explicitly handling the sign of the most significant bit in the partial product computation. For this purpose, each operand is analyzed, and if it is negative, the minus sign is explicitly prepended to the left of its most significant bit. Then, the partial product matrix is computed by performing bitwise multiplication and using the standard rules of decimal numbers. Multiplying by 0 results in 0, multiplying two bits with opposite signs results in -1, and multiplying two bits with the same sign results in 1. Note that the remaining combinations are omitted in this slide for the sake of brevity, since they can be obtained by applying the commutative property. Finally, no sign extension of the individual partial product rows is performed. Here we show an example of this first part of the process, using the operands -13 and -11. We add the minus sign to both of the most significant bits, since the two operands are negative, and we compute the partial product matrix according to the rules discussed above. The method continues by decomposing the partial product matrix into two submatrices. The first submatrix contains only positive terms, with negative ones replaced by zeros, while the second one contains only negative terms, with the positive ones replaced by zeros. Note that in the negative submatrix, minus symbols are removed. Then the result of each submatrix is computed, thus obtaining two natural numbers, namely r plus and r minus. They represent the positive and negative contributions to the final result, respectively. Note that the M minus submatrix is almost entirely composed of zeros, except for the elements in the last row and along the leftmost diagonal, excluding the leftmost bit. By duality, the M plus submatrix includes all remaining elements of the partial product matrix. This aspect considerably reduces the number of carries in the computation of the sum, especially for the M minus submatrix, thus enabling potential optimizations in the circuit implementation. Finally, each of these two values is converted to 2's complement by appending a 0 on the left of the bit string, and the overall result is obtained by subtracting r minus from r plus. Let's continue the previous example. We separate the bits of the computed partial product matrix, thus obtaining M plus and M minus. It is worth noting that, by construction, only the elements highlighted in orange belong to the M minus submatrix, while all other elements are included in the M plus submatrix. Then we compute the sum of each of them, obtaining r plus and r minus, and we append a 0 to the left of each of them, as shown in red. Finally, we compute the final subtraction step in 2's complement. In the hardware implementation of this method, the module does not need to explicitly compute the sign, since, as shown in the example, it is known a priori which submatrix each element belongs to. This allows the use of standard AND gates to compute the bitwise product and enables automatic separation into the two submatrices. Moreover, the circuit comprises components to compute the sum of the submatrices, based on the discussed architectures for unsigned integers and possibly exploiting the discussed submatrix sparsity, and the final subtraction in 2's complement. Another technique used to perform multiplication of numbers in 2's complement is the Booth method. We introduce the method by considering an example where we multiply a value m by q, which is equal to 30. As shown in the first equation, we can rewrite 30 as 32 minus 2. In this way, we obtain a sum of terms, each of which is a power of 2, possibly with a negative sign. At this point, we can apply the distributive property. In the second equation, we express the same computation in 2's complement form. Here, we also notice that the minus sign can be incorporated into the opposite of the m value. From these equations, we can draw the following observations. Q is decomposed into a set of powers of 2, and in binary format, multiplying by a power of 2 corresponds to a left shift of the multiplicand. Moreover, each power of 2 is multiplied by either the multiplicand or its opposite. Finally, the result can be obtained as the sum of all these terms. Starting from the decomposition introduced in the previous example, we can introduce the Booth method. Without getting into the details of the theoretical proof, such a decomposition can be automated by recoding the multiplier q as follows. Starting from the left, we examine each bit, I, together with the next bit, I minus 1. If they are equal, the bit is recoded as 0, as shown in the first and last rows of the table. If the bit is 0 and the next bit is 1, the bit is recoded as plus 1. And if the bit is 1 and the next bit is 0, it is recoded as minus 1. Finally, to encode the last bit, an additional 0 is assumed to follow the bit string representing the original multiplier. The partial product matrix is then computed by considering the original multiplicand m and the Booth-encoded multiplier q, which have n and k bits respectively. If the bit I of the multiplier is 0, we fill the corresponding row of the matrix with a string of zeros. If the bit is plus 1, we place m in the row, while if the bit is minus 1, we place minus m. Moreover, as usual, each row I is shifted to the left by I positions, and we apply 2's complement sign extension to the value of each row to obtain n plus k bits. Finally, the standard method for unsigned integers is used to compute the result from the partial product matrix. Let's multiply minus 13 by minus 9. We first represent the two operands in 2's complement. We also compute plus 13, which is the opposite of the multiplicand, and the Booth-encoded multiplier. We analyze pairs of consecutive bits, and the last bit is analyzed with respect to a 0 shown in brackets. Then, we compute the multiplication of m by the Booth-encoded q. For the sake of clarity, on the left of each row of the partial product matrix, we indicate which value is used, and the sign extension is shown in red. The result is obtained by performing the standard sum of the matrix elements. The hardware implementation of this method is quite simple. A combinational circuit is used to compute the negation of m. Then, for each row, a multiplexer selects the value to choose among 0, m, and minus m, based on an on-the-fly analysis of the corresponding pair of bits of the original multiplier q. Finally, the sum of the partial product matrix can be performed by any architecture used for unsigned integer multiplication.